Hello friends, this is AKHILESH Pandey and in this lecture number 10 of the network analysis, I am going to introduce the superposition theorem. And before understanding the superposition theorem, we will first understand that where the superposition theorem is applicable, and then we will understand that in which type of circuit it is useful, and then after we will see the statement related to the superposition theorem, and then we will solve some problems related to superposition theorem. So here I am going to start the superposition theorem. Here it is. Okay, so the superposition theorem, the theorem is applicable to only those circuits that have linear and bidirectional element. The statement is that it is applicable to circuit having linear and bidirectional element. We are already familiar with these terms, linear and bidirectional. Linear element, the element having voltage current graph as linear will be called the linear element, and bidirectional means the property of the element does not change with the direction of flow of current, means it is independent of the direction of flow of current. So the elements that we have studied, the resistance, inductance and capacitance, these all lie in this category, linear and bidirectional elements. So the circuit having these elements, means resistance, inductance, capacitance, the superposition theorem will be applicable. But if we will talk about diode, the circuit having diode or BJT, these type of things, then for that circuit superposition theorem is not applicable, because that type of circuit is not bidirectional or linear. So the first fundamental is clear about the superposition theorem, that it is applicable only to those circuits that is having linear and bidirectional element. Now come to the next point, and for which circuit it is being used mostly. So mostly the superposition theorem is used for the circuit that have more number of sources, means there is more number of sources but the response is required for the single element. Means if a circuit having more number of sources, just for an example, we can check here. Here we have one voltage source V1 and the other voltage source V2, the current source also we have I. So if the circuit is like this, means where we have two voltage sources, a current source, or more than this number as well, means if we have a circuit which having more number of sources and only the current is required through this branch, we can see that current is required through R3 only, means current is required, or the response, means response may be either voltage or current. So if the response is required through only single element, then for that circuit we will use superposition theorem mostly. Means superposition theorem is used for those circuit mostly which has more number of sources but the response in an element is required for single element, means response is required for single element but there is more number of sources. Then that type of circuit, for that type of circuit we will apply superposition theorem. Okay, so this is not the required condition, this is mostly useful for that type of question. It will be mostly useful, and this is must, means it is applicable only to this type of circuit. Now come to the last, the statement of the superposition theorem. So the superposition theorem is actually it can be stated like the net response of an element will be equal to the algebraic sum of responses due to individual sources. Net response will be equal to algebraic sum of responses due to individual sources. Means here we can see that we have to find the total current through R3. Okay, and we have three different sources. Here we have V1, here we have V2, here we have I current. Okay, so for getting the net response, means the net current through R3, what we will do, we will put only one individual sources one by one. Means we will first take V1, then we will take current I, and then finally we will take V2. And whatever the responses due to V1 individually and I individually and V2 individually, we will sum these all and the total sum will be given as the net current through R3. Means what we will do, we will at the first step we will deactivate these two. Means deactivating current means open it. So we have only, for the first time we have only V1 voltage source with R1 resistance, and here we will have R2 resistance, and it will be open circuited. Of course, deactivating it we will get it. Okay, and next we have R3 here, and we have to find the current. Means I am just checking it, I dash. Okay, next, okay, there will be no any voltage source because we are deactivating these two, so it will be short circuited. So by short circuiting it, we will get this I dash result. Similarly, we will apply I individually and deactivate these two. So deactivating means short circuiting this one with R1 here and R2 here, and current will be active this time only. The current source is active only. R3 is here, and of course this will be short circuited again. Means we are deactivating this voltage source as well. So if we have the current I double dash, and similarly we will deactivate these two and find the response due to this V2. So we will have the circuit like this. Okay, fine. We will deactivate the V1. Deactivating V1 means short circuiting it. This is R1 only. Okay, we have R1, and this is R2. R2 we will write here, and this is open circuit because deactivated, current has been deactivated. Now the R3 we will write similarly, and the only source will be active this time, plus minus V2. So, and the response due to this, we will say it I triple dash. Okay, so by solving, simple applying KCL or KVL in these branches, we will get I dash, we will get I double dash, and we will get I triple dash. And of course, the net response will be algebraic sum of responses due to individual sources. Means individual response is this and this. So the net response, means the net current will be equal to I dash plus I double dash plus I triple dash. So this is the net current due to the individual sources. First time V1 was activated and rest was deactivated. Second time I was activated and rest was deactivated, and last V2 was activated and rest was deactivated. So this is the process to find the current through any branch or voltage. Similarly, we can find the voltage across any branch using the superposition theorem. So overall, the overview about the superposition theorem is that it is applicable to linear and bidirectional element. It is mostly used in those circuits which have more number of sources, but the response in single element is required, and the net response is given by algebraic sum of individual response due to individual sources. Now we will see some example related to the superposition theorem. So here we have the example related to superposition theorem. So let's check the example. Okay, so this is the circuit that we have here. There is 2 ohm resistance and one 6 volt source, voltage source of course, and 1 ohm resistance. Okay, and finally we have 2 ohm resistance with 2 ampere current. Okay, so we have 2 ampere current. Now we have to determine the current in this branch. I is okay. So we can apply here superposition theorem because we can see that 6 volt is source, one source is here, one source is here. We will apply these sources, means activate these sources one by one. Means once we will activate this and deactivate this, next time this will be activated and this will be deactivated, and the responses due to individual sources will be taken here and that will be summed up. Let's see. First, activating this one. Okay, 2 ohm, 6 volt, 6 volt we have, 1 ohm, and the current is I dash. I'm supposing it that the current is I dash. Okay, Here it is 2 ohm and it has been deactivated because one indivisible source has been taken once. Okay, it has been deactivated, means it is open circuit. Okay, fine. I dash we have to determine very easily. We can determine it because there is no any 2 ohm. There will be no any calculation of this 2 ohm because it will be having ignored because there is no any current through this branch. So it has been ignored. It has been ignored. Okay, and now we are left with this circuit only. So applying simply KVL in this branch, we will get I dash equals to 6 upon 2 plus 1 3, and that will be 2 ampere. So the first result, I dash equals to 2 ampere. Next, what we will do? We will deactivate this. Deactivating voltage source means short circuiting it. Okay, so 2 ohm and it will be short circuited, and the rest we have 1 ohm here, and this time we will assume it I double dash, and here we have 2 ohm and 2 ampere current source. Okay, and due to this 2 ampere current source, we will find I double dash. We will try to find I double dash. So how we can find it? 2 ampere, and it is being distributed in the two branches. One having the resistance 2 ohm and the other having resistance 1 ohm. So simple current division rule, and the direction is opposite. So I double dash will be negative of this. So I double dash equals to negative of 2 into the resistance will be multiplied. It will be this one, it will be multiplied, and the sum of the two, that is 2 plus 1, so minus 4 by 3. So I double dash we got minus 4 by 3 ampere, and I dash we got 2 ampere. So overall the net current through this will be the summation of I dash plus I double dash. So value of I dash is 2 ampere plus I double dash is minus 4 by 3. So overall we get the result 3 minus 6 minus 4, it means 2 by 3 ampere. So this is the this is the final result of the given problem, and I double dash, as we can see here, minus 2 into 2 minus 4 by 3, and here we can see that I dash is 2 ampere. So overall the net current will be the current due to individual sources. So first time we considered 6 volt, and the second time we considered only 2 ampere. So by by adding the individual responses, we got the final net current. Similarly, we can solve some other circuit related to where we can apply the superposition theorem. One more question we will see where there is a dependent source in the circuit, and we will try to find the voltage across some element. Okay, so let's check the question first. So here we have the question related to superposition theorem, and the question is, here we have 2 ohm, okay, and 2 voltage source is here, plus minus of course, and the rest here will be 2 ampere current source here. Okay, lastly here is this 2 ohm, and there is one dependent source Vx. Okay, and here the Vx is here. The drop, whatever the drop will be, it is plus and it is minus. Okay, so whatever the drop across 2 ohm will be the same voltage source will appear here. So here we can see that we have a dependent source. But for this type of circuit, how we will apply the superposition theorem? So there is no any special treatment to this voltage source, means this dependent source. Means dependent source will be included in the circuit like element. Dependent source will be treated like element. Will be treated like an element. So there will be no any special treatment for this dependent source. Instead we will treat it like a single, means treat it like an element, and we will solve the entire circuit with the methodology that we have studied in the last question. So the first step, what we will do, we will consider this voltage source only. So considering this voltage source, we have 2 ohm here, and The voltage source has been considered 2 volt and rest 2 ampere open circuited. Okay, because deactivating current source means open circuited. Okay, 2 ohm we have, and here we have the voltage source, dependent voltage source actually, and it will be included in the circuit itself, and here it is plus minus Vx. Okay. So what we have to determine, actually the question was to determine Vx itself. So we have to determine Vx itself. Okay. So due to this voltage source only, what will be the Vx? So just applying the KVL in this loop, 2 minus Vx and the current will be Vx by 2. Current through this branch will be Vx by 2. Simple calculation. Voltage by resistance, Vx by 2. Okay, that current will flow through this. Okay, so the drop will be here again minus Vx by 2 into 2, of course, and again minus Vx, the exiting polarity I am taking. So 2 minus Vx minus Vx minus Vx. So overall Vx equals to 2 upon 3. 2 upon 3 volts. So first we have got the result Vx, and instead we will say it like Vx dash. So it will become Vx dash, of course. So Vx dash is 2 by 3 volt. Now the next time we will deactivate this voltage source and consider this current source only. Okay, so current source only 2 ohm again we have, and the voltage source will be short circuited, and here we have plus minus Vx, and the current source will be considered only, that is 2 ampere, and this is 2 ohm, and we will have plus minus Vx, double dash we will take, and this will be double dash. Okay. So due to this 2 ampere, what we can find, we have to find the Vx. Okay, so plus minus Vx we can consider it as ground, and applying the nodal analysis at this point means KCL, simple KCL we will apply. So it is plus minus Vx dash double dash, it means minus Vx double dash will be the potential at this level. Okay, so writing the KCL simply, so minus Vx double dash divided by 2 minus 2 the incoming current, and minus Vx double dash minus Vx double dash, so minus 2 Vx double dash divided by 2 equals to 0. So simply we can write it, and minus Vx double dash by 2, so minus 3 Vx double dash by 2 will be equals to 2. So overall we will get Vx double dash equals to minus 4 by 3 volt. Okay, easy calculation. Minus 3 Vx double dash by 2 equals to 2. So 2 into 2 4 minus 4 by 3. So Vx double dash equals to minus 4 by 3. So Vx dash we have got 2 by 3, Vx double dash we got minus 4 by 3. So overall, by summing these two, Vx dash and Vx double dash, we can easily get this Vx. Vx we can get easily, Vx dash plus Vx double dash means Vx dash is 2 by 3 and Vx double dash is minus 4 by 3. So the result will be 2 by 3 minus 4 by 3. The result will be 3 here, 2 minus 4 or minus 2 by 3. So Vx is minus 2 by 3 volt. So overall, in this way we can calculate the total voltage across any branch, and if there is dependent source, then that dependent source will be treated like a simple element, means it will be included in the circuit itself, and if this voltage across an element will change, and that voltage drop will be similarly activated, means similar voltage source will be applied here because it is dependent on this voltage drop. So overall, the superposition theorem is applicable to both dependent and independent type of sources, and here we can see the example. Okay, and the last point related to the superposition theorem is actually the homogeneity principle. So we will see that how the homogeneity principle can be concluded using the superposition theorem. So what homogeneity principle actually says, let's check. So here we have homogeneity principle. So according to this principle, if we have any voltage source, means if there is any excitation and there are so many resistance R1, R2, some R3 is here, some R4 is here, and so many other sources, other elements may be in the circuit. So as per the superposition theorem, we see that the voltage sources, means the individual sources was applied once, and the total value due to the all the sources will be the algebraic sum of the individual sources, means algebraic sum of the response due to the individual sources. So similar to that, if we have one voltage source, just considering we have a single voltage source V, and there will be of course some responses here, means if I am considering what this V1, then that will be V1 some value, V2 we will have some value. So if instead of V I apply 2V, means I am just scaling it by a factor 2, then what will be the individual responses, what will be the effect on the individual response? So that is the principle, that is the homogeneity principle. And as per the superposition theorem, we just see that if two similar voltage sources will be added here, means due to one voltage source we have got the result V1. So due to the other voltage source, the same voltage source, we will get the result again the V1. And if we will sum it up, means if we will sum the two voltage sources, means V1 will be summed up with V1 itself, then the result will be of course 2V1. Means we can see that when we are applying scaling it by 2, the response is again scaled up by 2. So that is the homogeneity principle, that if any voltage source or any source, any excitation you can say, is scaled up by any scaling factor k, then all the elements we will see the same scaling factor, means see the same scaling factor in their response, means their responses will be also scaled up with the same scaling factor. So this is the homogeneity principle, and this can be derived from the superposition theorem. So that's all about the superposition theorem, and we will see some other topics related to the network analysis in the coming class. Thank you so much for watching, and